All right, so today we're going to talk about chemical changes. We said that chemistry is a study of matter from an atomic perspective. Our goal and what we want to do in chemistry is to understand the behavior of matter. Ultimately, what we really want is to be able, as far as chemistry is concerned, what makes the study really chemistry is that we're interested in the transformation of matter. We want to be able to manipulate it to do things that we want it to do. Okay, so let's talk about chemical changes because that's how we accomplish that. First of all, difference between physical versus chemical change. Uh, Chemical change is defined as a transformation of one or more substances to other substances. So in other words, you're looking at a change in composition, okay? If there is no change in composition, then there's no transformation from one substance to another, then that change is just a physical change. So examples of physical changes would be like the phase changes that we talked about before, like melting, vaporization, condensation. Those are just physical changes. A chemical change has to involve a transformation. So that means you'll have to observe a decrease in the amount of one or more substances and an increase in the amount of some other substance or substances. So the amount of the substances that disappear or becomes less as the change occurs would be what we would call reactants, and we use the word products to refer to the substances that they're transformed into. Okay, so here's an example. Suppose you have a drop of water, you add it to a white solid, and you got a blue solid, dry, not wet, okay? So the white solid was dry, you add water to it, and it became a blue solid that was also dry. What would be your reactants and products here? So your reactants would be the water and the white solid. Those would be your reactants. They are transformed into the blue solid, so your blue solid would be your product. In fact, this is what you would observe in the lab if you were to do this reaction. Copper sulfate. Uh, Copper sulfate is a white solid. Okay, is a white solid, and if you add water to it, you get another solid, a blue solid, which is copper sulfate pentahydrate. This is a blue solid. So this is what you get when you put together copper sulfate and water, you get another compound, the hydrate. Alright. Now, during a chemical change, we say the amount of a substance X, suppose it went from 5 grams to 6 grams. Is this a reactant or a product? What would be the answer to this one? Uh, let's make this a clicker question. Are we ready to do a clicker? So is it A, a reactant, or B, a product? Okay, it went from 5 to 6. If you had more of it now, then that means it must be a product of the reaction. Okay, a reactant disappears over time. A product increases over time. Okay, so you'll be transforming reactants to products. So you'll have less of your reactants after a while, and you'll have more of your products after a while. Okay, correct answer for that one is B. Let's look at a chemical change now from an atomic perspective. A chemical change does not involve destruction or creation of atoms. It simply involves a rearrangement of atoms in the way they're organized. So bonds between atoms get broken and new bonds are formed. So for example, in this particular case, is this a chemical or a physical change in this pictorial representation of what's going on at the atomic level? So is this A, a chemical change, or B, a physical change? Okay, yes, this is a chemical change because as you can see, you no longer have these. It appears these have their bonds broken, right? And so you have these two extra free atoms here, and now you don't have these diatomic molecules on the product side. So these would be, I think this would be an example of a product, okay? And so would this one, okay? The triatomic molecules over here on the left would be what we would call reactant molecules. Alright, so let's look at an example here. Let's look at the pictorial representation here for a chemical change. Chemical change is involved here. What are the reactants and what are the products and which molecules are not involved in the reaction? Let's take a look. This pair right here of two little circles would be a pair of hydrogen atoms, so that would be H2, okay? Do we have any H2s on the product side, on the after side, I'm sorry. So this is before the reaction occurred, this is after. The picture over on the right is a picture of a representation of the reaction mixture after the reaction has occurred. So you can see there's no H2 on the right. So you have 1, 2, 3 H2s on the left. Okay, so before, I'm going to call this before. You have 3 H2s. After, you have none. So would this be considered reactants or products? That would be reactant, okay? You have less of it. Now, in fact, you don't have any more H2 after the change has occurred. Let's see what else we have in this picture. This one right here, that's a pair of oxygen atoms. So that's an O2 molecule. How many do we have on the left before the change occurred? You got 1, 2, 3, 4, 5. 5 before the change occurred. After, you have 1, 2, 3. Okay? So is this a reactant or a product? Or is it both? It's still a reactant. Okay? It can't possibly be a reactant and a product at the same time. If you have more of it, then it's a product. If you have less of it after the change, then it's a reactant. Let's look at what else we have here. Okay, this one right here, that's 2 hydrogens and an oxygen, so that's H2O. That's a water molecule. Okay, so we have a water molecule. Let's extend this page. H2O. How many do you have before the change occurred? 1, 2, and that's it. So 2 water molecules before the reaction occurred. After the reaction occurred, what happens? You now have 1, 2, 3, 4, 5, 6 water molecules. Okay? So that's 6 water molecules. Is water then a reactant or a product? Right, it's a product. You have now more of it. What about the other one here? Oops. I miscounted my hydrogen. I forgot there's an extra one over here. Okay, so we have 4 hydrogens before. Okay, 4 hydrogen, 4 H2s before. All right, let's look at the last one, which is going to be this one right here. So 1, 2, 3. What are these? These are pairs of nitrogen atoms. So I'm going to put an X on it so to distinguish it from the H2. So there's 3 of those, 3 N2s on the left. before the change occurred. And how many do you have on the right? You still have 1, 2, and 3. Okay? So N2 in this case, nothing happened to N2. So this is not a reactant or a product. So this is what you might call just a spectator molecule in this case. It just happens to be there. It's not really involved in the reaction. So what happened here? Overall, we say that what? 4 molecules of H2, right, disappeared, right? And we said that 2 molecules, so you lost 4 molecules of H2, you lost 2 molecules of O2, and you made 4 molecules of water. So we can represent this change by what's called a chemical equation. We can say that 4 moles of H2 reacted with 2 moles of O2 to give us 4 molecules of H2 reacted with 2 molecules of O2 to give us 4 molecules of H2O. So this is one example of what's called a balanced chemical equation. So this is an example of what we call a chemical equation, which represents the chemical change. Okay? You'll notice nothing has changed in terms of the number of atoms. If you were to go back and forth here, okay, you count the number of atoms before and after the change has occurred, you get the same number of atoms. Let's count your hydrogen atoms. You have 2, 4, 6, 8, okay, and then there's 10 and 12. You have 12 hydrogens on the left. Okay, on the right you still have 2, 4, 6, 8, 10, 12. 12 hydrogens on the right. Okay, before and after, the number of atoms remain the same. The oxygen, how many do you have? 2, 4, 6, 8, 10, plus an extra one, that's 11, and another one, that's 12 also. After the reaction, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You still have 12. Okay? And then for the nitrogen, you have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So the law of, this is known as the law of conservation of mass. During a chemical change, the mass doesn't change. Total mass of reactants is equal to the total mass of the products. So, and interpret that to mean that no atoms are destroyed, no atoms are created. What simply happens in a chemical change is the atoms rearrange the way they are organized. Okay? So if you look at this chemical equation that we have here, okay, what I did was I wrote the formulas of the reactants on the left and the formulas on the products on the right, and I indicated by a number in front how many molecules are involved. Okay, so here 4 molecules of H2, that's a total of 8 hydrogen atoms. 4 times 2 is 8, right? And 4 times 2 here is also 8. That means you have 8 hydrogen atoms that were transformed from being part of H2 molecules to being part of H2O molecules. Okay, so if you multiply the number in front of the formula, that's called the coefficient, by the subscript, you get the count for the number of atoms that were involved in a chemical change. Note that the nitrogen doesn't appear here because a chemical equation simply tells you what happened. Nothing really happened to the nitrogens in this representation of the reaction. Okay? So, to summarize, a chemical equation, like I said, is a symbolic representation for a chemical change. So here's another example of a chemical equation. You have calcium carbonate plus 2HCl. So this is what happens if you were to mix chalk and hydrochloric acid. You're going to get calcium chloride, water, and CO2, carbon dioxide gas. If you did this in the lab, you'll see bubbles of carbon dioxide. Okay, same type of reaction you'll see if you mix like baking soda and vinegar. That's carbonate and an acid. Will give you bubbles of carbon dioxide. That's the fizz that you see. Okay, in a chemical equation, the formulas of the reactants are written on the left. So in this case, calcium carbonate and HCl are the reactants. formulas of products are shown on the right. So our products here are calcium chloride, water, and carbon dioxide. And in addition to the formulas of reactants and products, okay, you write numbers in front of the formulas like this two right here. This is what's called a coefficient. Okay? And if there is no coefficient written, it's implied to be 1. So the coefficient of calcium carbonate here is implied to be 1. There's none written in front of calcium chloride, so that coefficient is implied to be 1. In front of water, there's a coefficient of 1 that's implied. In front of CO2, there's a coefficient of 1 that's implied. If you want a more complete description of the reaction, you can also specify the physical states of the reactants and products when the reaction was carried out. So in this case, we said we were dealing with a calcium carbonate sample that was a solid. Your HCl, the AQ label means it's in aqueous solution that's mixed with water. Okay. Same thing with the calcium chloride product. And we said that the water that was formed simply joined the rest of the water that was in the aqueous solution. So it's part of the liquid. So L stands for liquid. And the G here stands for gas. That means the carbon dioxide that was formed was in the gaseous state. Okay? So that's what a chemical equation is. Question? All right. Now, like I said, a chemical equation has to be balanced. By that we mean that we should write these coefficients. So the purpose of these coefficients is to make sure that the number of atoms of each kind is the same on the left side of the arrow and on the right side of the arrow. Okay? And if to count atoms before and after the reaction on both sides, you simply multiply the subscript of whatever element you're interested in by the coefficient. So, for example, let's look at this chemical equation again. How many chlorine atoms are shown on either side of the arrow? Let's verify that the reaction is balanced. Well, let's look at chlorine. Okay, so chlorine appears in HCl. The subscript of chlorine in HCl is implied to be 1. So 2 times 1, there's 2 chlorine atoms on the left. On the right, the coefficient of chlorine appears in calcium chloride. That's the only place you see chlorine, and the coefficient of calcium chloride is 1. The subscript of chlorine in calcium chloride is 2. So on the right side, the number of chlorine atoms shown is 1 times 2, or that's equal to 2. So you see chlorine is balanced. Let's verify everything else is balanced. Calcium on the left, 1 times 1, that's 1. On the right, you have 1 times 1. You also have 1 calcium atom on the right. Carbon, you have 1 carbon on the left, 1 times 1. And on the right, you also have 1 carbon, 1 times 1. So carbon, you say, is balanced as far as this chemical equation is concerned. What else do we have here? Oxygen. On the left, you have 1 times 3. So you have 3 oxygen atoms. On the right, you have 1 times 1. And the oxygen here, you have 1 times 2. Okay, so that's 1 times 1 plus 1 times 2. There are 2 places where you find oxygen on the right, in H2O and CO2. So that's 1 plus 2. There's also 3 oxygen atoms on the right. So oxygen is also balanced. And finally, let's look at hydrogen. Hydrogen, we say, you have 2 times 1. Coefficient is 2. Subscript of hydrogen is 1. That gives you 2. On the right, you have 1 times 2. It shows up only in water. So 1 times 2 is 2. So we say that this chemical equation is balanced. Okay? The coefficients are written such that total number of atoms of each kind on either side of the either side of the arrow is the same. All right. Now, one thing to realize about balance equation is that the coefficients that you need, those numbers you write in front of the formulas, is not unique in order to balance the equation. For example, okay, this is the balance equation we had earlier. I can multiply all of these coefficients by 2. So I can write 2 calcium carbonate plus 4 HCl. Okay, one, remember the coefficient there is 1 for calcium carbonate. Multiply this by 2, that's a 4. Multiply this by 2, that's going to be a 2. And multiply this coefficient by 2, so that's going to be 2H2O. And multiply that coefficient by 2, that's going to be 2CO2. If you check the number of atoms on both sides of this, it's still a balanced equation. There's nothing wrong with this balanced equation, this equation right here. Okay? It just so happens in this case that you have a common factor for all your coefficients, but it doesn't really matter. It's still a balanced equation. Okay? What if I were to change my coefficient for HCl to 6? What if I were to make this 6 HCl? What would it take to still have a balanced equation? What did I do to get 2 to become 6? I multiplied by 3. So I can still get a balanced equation if I multiply all the other coefficients by 3. So I can write 3 calcium carbonate plus 6 HCl gives me 3 calcium chloride plus 3 H2Os plus 3 CO2s. Okay, so you can see for yourself, check the numbers, you'll find that this equation is still balanced. So there isn't a unique way to balance a chemical equation. Now, typically what we'd like to do, but it's not a requirement, is we like to use the smallest possible set of whole numbers. And so typically this equation, you'll see this written this way, with the lowest possible set of whole number coefficients. Okay? So sometimes you'll encounter on a test, you might see this without the coefficients, and then the question would say, when this equation is balanced, what's the coefficient of HCl? Okay? So you might see this on the test without the 2 there, and then the question might say, what would be the coefficient of HCl if this is balanced? Then the answer can be anything. It can be 2 if you put a 1 in front of all the others. It can be 4 if you put 2 in front of all the others. So it's not unique, okay? When you do encounter a question like that, you can, chances are, correct answer is 2. You pretty much just have to assume that the intent was to ask for the case where you have the smallest possible set of whole numbers. Okay, some questions are more carefully written, some are not. So in those cases, you can just take that to mean that whoever wrote the question's intent was to ask for the coefficients in the balance equation with the smallest set of whole numbers. But like I said, there isn't a unique way of balancing a chemical equation. Once you find one way, then there's an infinite number of other ways of balancing the chemical equation. Okay, so it's customary, but it's not necessary to use the smallest set of whole numbers to balance a chemical equation. How can we tell you have the smallest set of whole numbers? You just if you can find a common factor among them, you divide them by the common factor. Okay? Or the way to tell if the smallest, they're all whole numbers and the smallest of those whole numbers is 1, then you're down to the lowest possible set of whole numbers. But if you can find a common factor that you can divide all the coefficients and still end up with a whole numbers, then you don't have the smallest number coefficients. Okay? So what you can do is you look at all your coefficients, pick the smallest one. If it's not a 1, divide all of the others by that smallest number, and you end up with non-whole numbers, then you already had it. So, for example, let's say these are the coefficients. Which of these, A, B, or C, can be reduced to a set of smaller whole numbers? Clicker question for this one? Okay, very good. This right here, if you divide by 3, okay, you get 1:2:2. 3 divided by 3 is 1, 2, 2. Whereas this one, if you divide by the smallest number, let's divide this by 2, you get 2.5, 1, 1.5, 2. So you can't get any smaller than these, okay? Whereas this one, 1's already the smallest whole number. You can't reduce it any further. So correct answer is C. All right. Now, you may encounter chemical equations that have fractional coefficient. It's okay to use fractions. There's nothing wrong with them. Okay. The important thing to realize, though, is that these fractions, when you see these fractions, they don't represent fractions of molecules. Okay. There's no such thing as half a molecule. So, like if you see a 1/2 in front of CO2, don't interpret that as half of a carbon dioxide molecule. Interpret that instead as half of a mole of molecules. Okay. And so half of a mole is still 300 billion trillion, okay, since a mole is 602 billion trillion atoms, atoms, molecules, or ions. Okay, so it's okay to use fractional coefficients as long as the numbers still balance out. Okay. So, for example, here's a balance equation that has fractional coefficients. Let's verify first that this is in fact balanced. 1/2 times 2, the nitrogen on the left, coefficient times subscript, 1/2 times 2 is 2. On the right, coefficient is 1, subscript is 1, 1 times 1, it's balanced. Hydrogen on the left is 3/2 times 2, okay? So that's going to be 3. And on the right side, your hydrogen is 1 times 3, it's still 3. So this equation is still balanced. If you happen to encounter a balance equation that has fractional coefficients, you can always change that to 1 with whole numbers. So what would we need to do to change this to a balance equation with whole numbers? We just look for the least common multiple of your denominator. So this 1/2, this 1/2. So the least common multiples of the denominator is 2. So multiply everything by 2. Okay. So 1/2 times 2 is 1, 3/2 times 2 is 3, and 1 times 2 is 2. So you can change your balance equation to 1N2 plus 3H2 gives you 2NH3. This is still a balance equation. This is the balance equation using the simplest set of whole numbers. Okay. There are some tips for balancing. Balancing, pretty much most reactions you can balance the equation by simply doing trial and error. Count the atoms on the left, count the atoms on the right, make adjustments. Here are some tips that you can use to quickly balance your equation. Always remember you have to adjust the coefficients only. Once you've established the formulas of your reactants and products, do not alter those. Okay? So you cannot be changing subscripts once you've established what they are. Okay, now it's also a good idea to first balance the elements that show up just once on both sides of the arrow. Okay, because then that would pretty much set those two numbers. If you change one, then you automatically know what the change for the other one would be. So start with elements that only show up once, because if it shows up more than one compound or more than one substance on one side, then you might not know which coefficient to adjust. Adjust the coefficients upward. Use the smallest possible whole number and you just keep bringing them up. Okay? And then every time you make an adjustment to your coefficient, always recheck that the atoms that you have previously balanced are still balanced. So here's an example. Let's just do this by trial and error. Okay, CH4 plus O2 gives you CO2 plus H2O. How many carbons do you have? This is not balanced right now. Let's see. Carbon, you have 1 times 1. So you have 1 on the left. And on the right, it shows up in CO2. So one coefficient of 1 times subscript of 1. You also have 1 on the right. Hydrogen, you have a coefficient of 1 for methane times 4 hydrogens in methane. You have 4 hydrogens on the left. And on the right, you have 1 water times 2, that gives you 2 on the right. So hydrogen is not balanced. So what should I do to balance the hydrogen? I need more hydrogens on the right, so I need more water on the right. How can I make the total hydrogens on the right equal to 4? I'm going to need 2 waters, right? 2 plus 2 gives me 4. So I'll put a coefficient of 2 in front of my water here. Oops. Let me fix that. So it's not 2 times 2. So this is now 4. And then I recheck my carbon. I still have 1 carbon on the left, and I still have 1 carbon on the right. So carbon is still okay. Finally, I check my oxygen. I have 1 times 2 on the left, and on the right I have 2 times 1. Plus, there's another one over here, which is 1 times 2. So that's a total of 4. Okay, so 2 on the left, 4 on the right. What should I do? I need more oxygen on the left. So I always adjust the low side, bring up the low side to match the higher side. So the left side has only 2. If I need 4, I need another pair of oxygen, so I need another O2, 2 O2s. Okay, so I can say I need 2 of those O2s to give me a total of 4, so I need 2 O2s right there. So my balance equation is, you can say CH4 plus 2 O2s yields 1 CO2 plus 2 H2O. Okay, so that's the balance equation right there. Right. Before we go into this one, let me show you the computer lab for chemical changes. This is there's some nice web resources that you can go to practice balancing chemical equations. Okay, so this would be a good practice. This one right here. So this is activity 3 in this handout. Again, this goes to the Colorado PHET simulation site in Colorado, balancing chemical equations. Okay. And what you need to do here is there are several games that you can play. It's really just a way to practice balancing chemical equations. Okay, so the example we just had was combustion of methane, so it's a good way to visualize what's going on. So if you have just one of each, okay, you can look at your balance scale. You can see you've got 1 carbon on this side. On the right side, you also have 1 carbon, okay? And your O2, you have 2 oxygens on the left, and you have 1, 2, 3 oxygens on the right, so oxygen's not balanced. So how did we balance our oxygen? We add more to the, okay, I think we did hydrogen first. Okay, so you have hydrogen, you have 1, 2, 3, 4 of those white spheres, 4 on the left, and on the right you have 2 hydrogens. So what we did to balance the hydrogen is we add more of this. Notice that all I have to do is change that coefficient right there, so now I have 2 waters. So that's 1, 2, 3, 4 hydrogens on the right, balances the hydrogens on the left. So carbon and hydrogen are balanced. And then the last thing that you need to balance is oxygen. So you have 1, 2, 3, 4 oxygens on the right, but you only have 2 on the left. So I increase the coefficient of my oxygen, and now I have a balance equation. Okay, there's a lot of balancing practice you can do here. So there's 3 different levels. You can play a game like this is level 3. Okay. So you can adjust your coefficients, and then you can check if you have a balance equation. So let's say I put a 1 there for all of them. If I check, it tells me it's not balanced, and it will show me why. Okay? So this is a good practice for you. All right. Now, you can make your balancing systematic if you don't like the idea of just trial and error going back and forth. You can actually use algebra to do this. So let me show you how it's done using this simple equation. This is simple. We've done this earlier by trial and error, but you can do this using algebra. You can say that, okay, the number of carbons on the left, okay, you represent your coefficients by letters. So W, X, Y, and Z are our coefficients here, okay? So you can say the number of carbons on the left is the coefficient of CH4 times its subscript, which is 1. So it's on the left, it's W. So to balance carbon, you have W carbons on the left. How many carbons do you have on the right? Subscript of carbon on the right is 1. So 1 times, and coefficient of CO2 is Y. So 1 times Y. So you know that W must be equal to Y. Okay? What this is saying is, whatever the coefficient of CH4 is, that's got to be the same coefficient as CO2. In fact, you can see that from our balance equation. Okay? 1 is 1 here, 1 CH4, 1 CO2. If I multiply this by 2, if I make this a 2, then the CO2 is going to have to be a 2 as well. If I change this to a 3, and then this will have to become a 3. So you can see whatever this coefficient for CH4 is, it's going to be the same as the coefficient for CO2. Mathematically, you say that W here must be equal to Y. To balance your hydrogen, then you say, okay, hydrogen on the left is 4 times W. And the hydrogen on the right is 2 times Z. Coefficient of water and times the subscript of hydrogen in water is 2, so that's 2Z. Okay, and finally, to balance oxygen, you say the number of oxygen on the left is 2 times X, so that's 2X. Right? And the number of oxygen on the right is 2 times Y plus 1 times Z. Okay? So using these, you can solve for the coefficients. All you have to do is assign value to any one of these letters. Okay? So it doesn't matter. Remember, we said there's not a unique way of solving this, of balancing an equation. So if you, so let's say we'll let W equals 1. Then automatically from this one right here, you can say that W equals Y, so 1 equals Y, right? So now we know Y is 1. So we know W is 1. So if W is 1, then you know Y must be 1. What else do we know? If W equals 1, then we can substitute W here. You can say 4 times W, so 4 times 1 must be equal to 2 times Z. So we can solve for Z. Divide both sides by 2. And so Z is equal to 4 times 1 divided by 2 is 2, right? So we know Z is 2. So what else? What's the only thing missing? X, right? Well, what's X? To solve for X, we know that 2X must be equal to 2Y plus Z. We know what Y is, we know what Z is, so we can solve for X. So how do we solve for X? We say, let me get rid of this. We say that 2X is equal to 2 times Y, Y is 1, okay, plus Z, Z is 2. So we say that 2X equals 2 plus 2, or we say that 2X equals 4, and so X must be equal to 2. Okay, so our balance equation would be W equals 1. So W equals 1. X is 2. Y is 1, and Z is 2. Okay? This becomes really useful if you have more complicated equations to balance. But you know, if you're stuck going back and forth doing trial and error, try algebra. You might be able to get to your balance equation faster. And if you did W equals 2 here instead, you're going to find that Y is going to be equal to 2, and you're going to find that Z is going to be equal to 4, and you're going to find that X is going to be equal to 4. It doesn't matter what number you pick. The idea, the trick is you do need to make sure that you assign a value to the one that is related to that is simply related to all the others. So like if I were to pick a value for x to begin with of 1, that won't allow me to solve for y or z or w right away. So that's not a good idea. Okay? But if you do substitute for a number for any one of these letters, you end up with the right number of algebraic equations to solve the remaining unknowns. Okay? So you can still use algebra to solve for the others, but there are some variables that are easier to assign to begin with than others. All right. Chemical versus physical change. Like I said, chemical change involves a change in composition. So how do you know a chemical change has occurred? You simply monitor substances that are present in the mixture. If you have something disappearing and another substance appearing, then you know you have a chemical change. Now, if you can explain the change, you cannot explain the change by simply saying that your atoms or your molecules just move closer together or farther apart from each other, then okay, did I say can or can't? If you have a change can be explained by saying that the formula units remain the same and all they did was move closer or farther apart, then you're most likely just dealing with a physical change. So we've already explained vaporization, melting, sublimation, those phase changes. Okay, the molecules remain intact there. They don't, the bonds are not broken, no new bonds are formed. So those are just physical changes. Okay, so there's some signs that a chemical change has occurred. If you see them around you, if you see an unusual color change, you know, like if you have something sitting on a table, it's green, and then, you know, over time it turns brown, then, you know, then that means something's going on there. That's a chemical change, okay? But if you mix like yellow dye and a blue dye, you get something green. Yellow and blue make green. That's not necessarily a chemical change, okay? But if you mix something yellow and something blue and you get red, then that's an unusual color change. Then most likely you're dealing with a chemical change. Change in odor, okay? Burning, production of heat and light is typically a chemical change. Precipitation is what happens when you mix two liquids and you suddenly get a solid, okay? And that's a good sign that a chemical change has occurred. If you mix two things and you smell something, that means it's forming a gas. One of the products is a gas that happens to have a characteristic odor. Or bubbles. If you see bubbles, that means a gas has been formed. You do note that these are just signs that a chemical change has occurred. To really verify if a change has occurred, you have to sort of be able to identify the substances. Okay, so now is it fair then to ask you a question on the test as to whether something is a chemical change or not? It has to do with familiarity with nature, with the things around you. So if you're expected to know something's a chemical change, then it would be a fair question on the test. But in general, being given a description is not necessarily a guarantee that you can say whether or not for sure it's a chemical change or not. Okay. Also, the absence of a visible change, okay, even if nothing seems to be happening, doesn't mean that no change has occurred. It could be that, you know, whatever product you're forming happens to be, you know, in terms of visuals, indistinguishable from your reactant. So that's also possible. Okay, so the only guarantee that you have to tell for sure whether there's a chemical change is to actually be able to monitor the substances that are in your sample. Okay. So examples of chemical change that you're expected to know would be, you know, food, okay, digestion of food or rotting of food. That's pretty much living things are just a chemical factory. It's just all chemical changes going on there. You have gasoline burning. That's burning would be an example of a chemical change. If stain fades when you treat it with bleach, then that's a chemical change. If it fades just because you have, like if you have a dye, you put more water in it, it gets lighter. That would be a physical change because you can explain that as the colored molecules just spreading out, so it's just less crowded. It looks like it's faded. Okay, but if you put something there and it fades without changing its volume very much, without spreading it out too much, then it's a good sign of a chemical change. Okay, physical changes, examples, like I said, boiling, just phase changes, melting, or just splitting something in half. Like if I were to split a chalk in two, that would just be a physical change. So here are some, are we supposed to end early today? There's a few clicker questions here, but I think this might be a good time to stop because I do have another class today. So, all right.